Hi everyone! In this video, we're going to master 3 essential vector operations once and for all. These operations are the foundation of many advanced calculations that appear later in theoretical mechanics. In this exercise, we'll focus on 3 key operations: the dot product, the cross product, and the scalar triple product. This will form the 3 main parts of the problem that we'll solve step by step. We are given 3 vectors, A, B, and C, expressed in the autonomial basis R, I, J, K. Each vector is defined by its coordinates in this basis. Let's get started. In part 1, which focuses on the dot product, we will answer 3 questions. First, compute the dot product of vectors A and B. Second, determine the magnitudes of vectors A, B, and C. And finally, find the angle between vectors A and B. Let's begin with the calculations. Now, let's move to the solutions. First, the dot product of vectors A and B. We compute it by multiplying the corresponding components and then adding the results together. After performing the calculations, we obtain A dot B equal minus 8. Next, let's determine the magnitudes of the vectors. For each vector, we apply the well-known formula, the square root of the sum of the squares of its components. After applying this formula, the magnitude of A is square 14, of B is square 21, of C is square 26. Now, let's determine the angle between vectors A and B. To do this, we use an important property of the dot product. The dot product equals the product of the magnitudes of vectors multiplied by the cosine of the angle between them. From this relation, we can express cosine of the angle. Replacing the numerical values gives cosine theta equal minus 0.466. Finally, taking the arc cosine, we obtain theta equals 111.8 degrees. So the angle between vectors A and B is approximately 112 degrees. Let's now move to part 2, which deals with the cross product. Here we'll answer 3 questions. First, determine the vector D equals A cross B. Second, verify that this vector is orthogonal to both A and B. And third, calculate the area of parallelogram formed by vectors A and B. Let's start with the vector calculation. Applying the cross product rule, we compute the vector D equals A cross B. After performing the determinant calculation, we obtain D equals minus 10, 7, 9. Now let's verify the orthogonality. A key property of the cross product is that the resulting vector is perpendicular to both original vectors. To confirm this, we compute the dot product of D with A and B. In both cases, the result is 0. Which confirms that D is orthogonal to A and also orthogonal to B. Now, let's compute the area of the parallelogram formed by vectors A and B. In vectors calculus, there is a very convenient rule. The magnitude of the cross product A cross B is exactly equal to area of the parallelogram formed by these vectors. So we simply compute the magnitude of D. After calculation, we obtain area equal 15.16 square unit. I remind you, if anything is unclear, feel free to leave a comment. I'll be happy to explain further. Let's now move to the last part of the exercise, which involves that scalar triple product. Here we'll compute the scalar triple product of A, B, and C, determine the volume of the 3-dimensional shape formed by these vectors, and finally check whether the vectors are coplanar, meaning they lie in the same plane. The scalar triple product can be written in 2 ways. One notation uses commas, often seen in French textbook, A, B, C. The other, more common in English, uses vectors operation, A dot product B cross C. After performing the calculation, we obtain 44 as result. This value also represents the volume of the parallelepiped formed by the three vectors E, B, and C. Since this volume is not zero, the vectors are not coplanar. And that's it. This exercise summarizes the fundamental operations of vector calculus that are widely used in mechanics and physics. These tools will definitely appear again in our upcoming applied mechanics exercises. Thanks for watching until the end, and see you soon in the next video.